Hello there, I'm Sam Hoare from Pharmacanics. In this video we're going to talk in detail about the data we get from GPCR signaling assays, specifically the pharmacological data we obtain and how we interpret the results. This video is the second part of a two-part series on the operational model of agonism, a powerful pharmacological model that helps us understand our data. In part 1, we introduced the operational model and explained it in simple terms. You can find this video on the Pharmacanics YouTube channel. Here in the graph, we have data from a GPCR signaling assay where an agonist compound is stimulating cyclic AMP generation via a GPCR. Here we are measuring this at 4 different levels of receptor expression. These data can be explained by the operational model of agonism, and today we are going to take a deep dive into this model to help us to understand why the data look the way they do in our GPCR signaling assays. Let's briefly recap the explanation of the operational model we went through in part 1 of this video series. Here is the operational model mechanism. The model assumes the agonist-receptor complex is an activator of signal transduction. The complex interacts with the signal transduction system, and that generates the signal here. This model makes total sense when we compare it with the known mechanisms of GPCR signal transduction. Here is a diagram of the mechanism of cyclic AMP generation stimulated by a GPCR. The agonist-receptor complex here couples to the signal transduction machinery. In this example, the signal transduction system consists of the GSG protein and adenylyl cyclase. Activation of the signal transduction system generates the response, which is cyclic AMP here. Based on this mechanism, the first assumption of the operational model is that the agonist-receptor complex is an activator of the signal transduction system. This assumption has an important consequence. That is, the magnitude of the signal is dependent on the concentration of the agonist-receptor complex. This, in turn, has another consequence. It means that the signal is dependent not only on the agonist concentration, but also on the receptor concentration. This makes sense. The agonist-receptor complex is comprised of the agonist and the receptor, so the concentration of the complex is dependent on the concentration of both components, the agonist and the receptor. This moves us beyond the idea that it's just the agonist concentration that defines the response, and now we understand that the receptor concentration matters too. This explains our data from the previous slide. It explains why the signal is dependent on the receptor level. The second assumption is that there is a limit to how much signal the receptor can stimulate. We can explain this with our cyclic AMP mechanism here. There is only so much cyclic AMP that the system can produce, because there's only so much G protein, there's only so much adenylyl cyclase. We could increase the receptor as much as we want, but at some point we reach a ceiling where the receptor concentration is sufficiently high that it saturates the signal transduction machinery. There is a physical limit to how much signal that the signal transduction system can generate. We can see that limit on our graph here. At this point, the receptor is saturating the system, and so we hit this ceiling level of cyclic AMP here. This ceiling level of signal is called the system maximum effect, and we will be returning to this soon. Now, in this video, we are going to take a deeper dive into the model. This will enable us to understand more deeply why the pharmacology data we obtain from GPCR signaling assays looks the way it does. I have found the best way to explore models is to simulate the data. With a data simulator, we can change the parameter values and see how this affects the data. This enables us to understand what the parameters mean and how they affect the results in our assays. I made a simple simulator in Excel for you to use, which is freely available from the link in the comments, and we will go through this in more detail later. This deeper understanding will also provide you with a foundation to engage the literature on the operational model, which can be really fascinating. We will return to the literature at the end of this video. To understand how the operational model works, we need to understand the parameters the model uses to describe GPCR signaling pharmacology. Fortunately, these parameters are based on basic biochemical concepts, and so they can be understood reasonably easily. To understand these parameters, we will need to look at the mechanisms and the resulting equations of the operational model. Here we're doing pharmacology theory. We start with our mechanism here, then we derive an equation that describes the signaling activity, then we simulate the data to understand how the system works. This is what we're going to do for the remainder of this video, so we can get a thorough understanding of GPCR signaling pharmacology. Let's walk through the mechanism and the equation. This will show us how the mechanistic assumptions of the operational model are expressed mathematically. Don't worry, this is reasonably straightforward. Here is our operational model mechanism. We have our agonist-receptor complex coupling to the signal transduction system to generate the signal. Now, we also need to include here the binding of the agonist to the receptor. Here we have this step illustrated. The agonist binds to the receptor to form the agonist-receptor complex. The strength of this interaction is defined by the agonist affinity constant, which is termed Ka. This is just the affinity, or Kd, of the agonist for the receptor. Let's start with this agonist binding step, because it is reasonably familiar to us pharmacologists. Here in the diagram now, we only have binding of the agonist to the receptor. Here we have the graph defining agonist binding. The agonist concentration is on the x-axis here, and the concentration of the agonist-receptor complex is on the y-axis, so this is a familiar binding curve. Here we have the equation that defines agonist binding to the receptor. Let's examine this so we understand it clearly. This equation defines the curve we see on the graph. It defines the agonist-receptor complex concentration on the y-axis here in terms of the agonist concentration on the x-axis. This curve is defined by two binding parameters. First, we have the affinity of the agonist for the receptor, which is Ka here. As you know, this is the concentration of agonist required to occupy 50% of the receptor population, which we have indicated on the graph here. Ka is 30 nanomolar in this example, which means the agonist binding affinity is 30 nanomolar. Second, we have the number of receptors available to bind the agonist, which we term R tot here. When we have enough agonist, we saturate the receptors, and so the plateau level here is equal to R tot. In this case, R tot is 10,000 receptors per cell, as you can see in the graph. Note that this equation is a saturation type equation. We can see the curve goes up, then reaches a limit where the receptor population is saturated by the agonist. In mathematical terms, this is called a rectangular hyperbola. We need an equation that defines the interaction of the agonist-receptor complex with the signal transduction system. Here is our mechanism diagram. Now let's isolate the signal generation step. Here we have just the agonist-receptor complex interacting with the signal transduction machinery to generate the signal. Let's see the graph representing this interaction. On the x-axis, we have the concentration of the agonist-receptor complex. Note that this is different from the graph on the previous slide. Here, the x-axis is not the agonist concentration, but instead it is the agonist-receptor complex concentration. On the y-axis, we have the signal being generated by the agonist-receptor complex. Now we need an equation that defines the amount of signal in terms of the concentration of agonist-receptor complex, and here it is. The operational model assumes this equation is a saturation type equation of the same mathematical form as the binding equation we saw on the previous slide. You can see this on the graph. As we increase the agonist-receptor complex concentration, we increase the level of signal. Then we reach a point where we saturate the signal generating capacity of the system, evident as this plateau here. In mathematical terms, this equation is a rectangular hyperbola. This is the primary advance of the operational model over previous pharmacological theories, this assumption that the equation here is a hyperbola. Let's look at this in more detail so we understand it better. The equation defines the magnitude of the signal, termed E on the y-axis here, which in this case is cyclic AMP. It defines this in terms of the concentration of agonist-receptor complex, which is on the x-axis here. Here we have the maximum signal that the agonist-receptor complex can produce, which we term EM. EM is the system maximum effect that we talked about earlier and that we will look at again soon. Remember, this is the maximum signal generating capacity of the system. As we increase the agonist-receptor complex concentration, it saturates the signal transduction machinery, reaching this ceiling level of signal the system can produce, which is EM. Now for the midpoint of the curve here. The equation assumes the agonist-receptor complex interacts with the system with a certain potency. This potency is termed Ke, and this is in units of agonist-receptor complex. Ke is the concentration of agonist-receptor complex required to produce 50% of the system maximum effect. This is evident from the graph here. In this example, the Ke value is 100 receptors per cell. This means we need 100 agonist-receptor complexes per cell to generate half the system maximum effect. We will revisit this parameter again in a moment so we can understand this better. One final thing, and it's a small detail regarding the equation here. We also include in the signaling equation a slope factor here termed N, which defines in effect the hill slope of the agonist-receptor complex interaction with the signaling system. You can read more about this in the original operational model paper here. Now we need the final equation for analyzing our data. To derive this, we need to combine both the equations we have just seen. Let's bring back our agonist binding step here. So here on the left is the binding graph we saw earlier, and here on the right we have the signaling graph. Now let's bring in our equations. Now let's get back to some experimental reality. These graphs are good for showing us how the operational model works, but they are not what we actually do in our experiments. Here's the graph showing what we actually do. We vary the agonist concentration on the x-axis and we measure the signal on the y-axis. So we need an equation which defines the signal E in terms of the agonist concentration A. Here we can see these variables in our equations, but they are separated into the two different equations. So we need to combine these equations. We take the equation for AR on the left and we substitute it into the equation for the signal on the right. After this, we do some rearranging to obtain the equation we need, which you can see here. The thing to note about this equation is this term here, R tot divided by Ke. This term defines the interaction of the agonist-receptor complex with the signal transduction system. It includes R tot, which indicates the signal is dependent on the receptor concentration. Then it includes Ke, which is the potency of the agonist-receptor complex for the signal transduction system. Note here that Ke is dependent on which agonist is bound to the receptor. Different agonists can stabilize the receptor in different conformations, and these conformations can have different potency for the signal transduction system. We will go through this more in a moment. This R tot over Ke term can be represented by a single parameter in the model, which is called tau. Tau is simply R tot divided by Ke. Tau is a global parameter defining the interaction of the agonist-receptor complex with the signal transduction system. The higher the value of tau, the stronger this interaction and the stronger the signal. We will see how this works in a moment. We can substitute R tot over Ke with tau in the equation. This gives us the form of the operational model equation we see in papers and textbooks. Now we have the equation, we can do some simulations to explain how the operational model works. You can do this yourselves with the simulator that is available at the link in the comments. You simply change the values in the green cells here and this updates the graph. Note that there are two tabs here. You can either simulate using tau or you can simulate using R tot and Ke. I have found that playing around with simulations is a great way to understand how the operational model works, and we're going to see some more examples. Let's look at the receptor concentration. To do this, let's use our graph from earlier. This shows the cyclic AMP signaling in response to an agonist named compound 1 on 4 different cell lines with different levels of receptor expression, from high to very low. Here are the values of R tot for the different cell lines, with expression level varying from 100,000 receptors per cell down to 170 receptors per cell. Here is the Ke value. The Ke value is the same in all cases because we are using the same agonist to activate the receptor. Remember, Ke is the potency of the agonist-receptor complex for the signal transduction machinery. In this case, the Ke value is 330 receptors per cell. We will look into Ke more on the next slide. Then here are the calculated tau values. Remember, tau is calculated simply as R tot divided by Ke. This means the higher the receptor concentration, the higher the value of tau, because R tot is on the top of this fraction. Here we see the calculated tau values vary from 300 for the high expressing cells down to 0.5 for the very low expressing cells. Now let's examine the Ke parameter. Ke defines how strongly the agonist-receptor complex couples to the signal transduction machinery. Here in our mechanism is the agonist-receptor complex, and here is the signal transduction machinery. Ke defines the strength of interaction between the two. This means Ke is dependent on the agonist that is bound to the receptor. Ke is the agonist efficacy parameter in the operational model. Specifically, Ke is the amount of agonist-receptor complex required to produce an effect that is 50% of the system maximum effect. We can illustrate this using some diagrams of receptor G-protein interaction, which is the first step of the signal transduction process. A weak agonist will produce a receptor conformation that only weakly interacts with G-protein. Here we see this weak interaction illustrated. The receptor conformation is not optimal for G-protein interaction. Because of this, we need a lot of agonist-receptor complex to generate the signal, since we are only weakly interacting with the signal transduction system, and this means we will have a high Ke value, for example 10,000 receptors per cell. This means we need 10,000 receptors per cell to generate half the system maximum response. At the other end of the spectrum, we have an agonist that strongly stimulates signaling. This compound produces a receptor conformation that strongly interacts with G-protein, as we see here. Consequently, we will need a lot less agonist-receptor complex to generate the signal, because this receptor conformation strongly interacts with the signal transduction system. This means we will have a low Ke value, for example 300 receptors per cell. This means we need 300 receptors per cell to generate half the system maximum response. Let's look at this in a bit more detail in the context of our signaling data. Here we have a partial agonist for the receptor, agonist 1, with an Emax that is 50% of the system maximum effect. Here the system maximum effect is shown by the dashed line. Here you can see the maximum for agonist 1 is 50% of the system maximum. Here in the table we have the R-tote and Ke values. The R-tote value is 10,000 receptors per cell. Here is the Ke value. Ke is the concentration of agonist receptor complex required to produce 50% of the system maximum effect. For agonist 1 here, the Ke value is 10,000 receptors per cell. This means we need to occupy all the receptors with the agonist to get to 50% of the system maximum effect. Let's look at this using our receptor conformation diagram like we did on the previous slide. The G-protein binding site is not in an ideal conformation to interact efficiently with the G-protein. So this interaction is weak and we don't get much G-protein activation. This means we need a lot of receptor to get enough G-proteins activated to reach half the system maximum. This means we have a high value of Ke here because we need a lot of receptor. Finally, we calculate the tau value here by dividing R-tote by Ke, and this gives us a value of 1. Now let's introduce an agonist with higher efficacy. This is agonist 2. Here you can see this almost reaches the system maximum effect. In our data table, you can see R-tote is the same as for agonist 1, and that's because we are using the same cell line. Here is the Ke value of 1000 receptors per cell. You can see the Ke is lower than the Ke of agonist 1. Remember that Ke is the concentration of agonist receptor complex required to produce 50% of the system maximum effect. This lower Ke value means we need a lower number of receptors to generate half the system maximum effect. The receptor conformation produced by agonist 2 is more efficient for interacting with G protein and generating the signal than agonist 1, so we need fewer receptors to generate the signal. Now let's look at our tau value. Remember, tau is R tot divided by Ke. This means the tau value is 10,000 divided by 1,000, giving the tau value of 10 for agonist 2. We note here, as Ke gets smaller, tau gets bigger, because Ke is on the bottom of this fraction here. Finally, let's look at an even higher efficacy agonist. Here we have agonist 3. This high efficacy agonist reaches the system maximum effect. Here we have a Ke value of 100 receptors per cell. This means we need even fewer receptors to generate half the system maximum effect. Agonist 3 is really efficient for generating the signal. In our receptor diagram here, we have the agonist 3 bound receptor, which is in an optimal conformation for interacting with the G protein. Here is the tau value of 100, which we calculate by dividing R tot by Ke. If you want a deeper dive on this, I recommend reading the original operational model paper at the link at the bottom here. One last thing these data show us is the difference between Emax and tau. Here are the Emax values for the three agonists. You can see agonists 2 and 3 are very similar in terms of Emax at 99% and 91%. However, when we quantify tau, we determine that the actual efficacy of the agonists is quite different, with agonist 3 being 10 times more active than agonist 2 here. This foundation we have been through here will enable you to engage with the literature on the operational model. These papers go deeper into the models and can explain some of the more sophisticated model behavior that we have not got into today. A literature search on operational model agonism will bring up many interesting studies for you to dig into. By way of an example, this paper here explains an observation we often see when we measure different signals at different steps down the same signaling pathway. Here we have illustrated our cyclic AMP pathway. We added here a downstream effect of cyclic AMP gene transcription changes. It turns out that the EC50 of an agonist is dependent on how far downstream we are from the receptor in the signaling pathway. Now let's look at the agonist concentration response curves for the different steps down this pathway. Here in green is the agonist curve for G protein activation, the most upstream response. We can see the agonist is rather weak, with an EC50 of 1 micromolar. However, when we measure cyclic AMP, a response which is one step downstream from G protein, we observe this agonist is more potent, with an EC50 of 50 nanomolar. Finally, when we look at an effect which is further downstream, gene transcription, the agonist is even more potent, with an EC50 of 3 nanomolar. This is a typical observation in GPCR pharmacology, as you may know. It results from there being consecutive steps of the pathway which acts to amplify the response. This results in less agonist receptor complex being required to generate the signal the further downstream we are from the receptor. And this effect is nicely explained in this paper here. In a second example, this paper here is an early example of analyzing data with the operational model to measure the model parameters. It is possible to quantify tau and Ka using curve-fitting methods. An equation is available to do this in the popular curve-fitting program GraphPad Prism, as you can see here. Here we have the results table from this analysis showing the Ka value here, and here are the tau values. This analysis provides robust agonist pharmacology parameters we can use in drug discovery, for example in translation to in vivo models and even prediction of human dosing. I have done this analysis for drug discovery projects and found it to be really useful. This brings us to the end of our presentation today. We have explored the operational model in detail, understanding the parameters of the model and how they affect GPCR signaling data. This foundation enables us to solve problems in our drug discovery and research projects and to explain GPCR pharmacology to our colleagues. We can use the operational model to simulate and analyze our data to better quantify the activity of our molecules. This can have important translational consequences as we advance these molecules into clinical trials. I hope this foundation will enable you to better understand and communicate our GPCR pharmacology data to help advance drug discovery and receptor research projects. Thank you very much for your interest and attention.